By 1942, the Eastern Front had become the deadliest theater of World War II. German forces, though highly trained and equipped, faced relentless Soviet counterattacks. Armored units were particularly formidable, with Soviet T-34 and KV tanks striking fear into infantry and disrupting supply lines. Conventional anti-tank weapons, PaK-36 and early PaK-40 guns, were often insufficient, especially during night operations or forested terrain. German commanders realized that survival required innovation beyond conventional artillery. Heavy tanks could outrun or outgun standard infantry weapons, and frontal attacks were extremely costly. Small, agile teams with clever tactics could be more effective than large-scale assaults. At this critical moment, German engineers began experimenting with an entirely new type of anti-tank weapon: magnetic mines. The goal was deceptively simple: disable or destroy enemy tanks without needing to face them directly. Soldiers could place these mines covertly on tanks during night raids, creating a sudden, localized advantage. The engineering teams faced numerous challenges. Early prototypes, often failed magnets, were too weak to adhere to dirty or moving vehicles, and explosives sometimes detonated prematurely. Nevertheless, each failure brought critical lessons. Engineers improved magnet strength, adjusted explosive charge placement, and refined fuse timing. This combination of ingenuity, persistence, and precise planning would soon allow small German teams to stop entire Soviet armored columns overnight, proving that tactical innovation could level the playing field, even against numerically superior forces. The idea of a magnetic mine was deceptively simple, but turning it into a reliable weapon required advanced engineering and meticulous testing. German engineers at Krupp and Rheinmetall laboratories began with basic principles. A strong magnet, capable of adhering to the steel hull of a tank, combined with a high explosive charge that could destroy or immobilize it. Early prototypes revealed significant obstacles. Magnets were often too weak to hold under movement or mud accumulation, and timed fuses frequently misfired. Engineers experimented with electromagnets, permanent magnets, and ferrous coatings to improve adhesion. They also calculated the precise amount of explosive needed to breach armor without overloading the device. Special attention was given to safety mechanisms. A premature detonation could kill the sapper, placing the mine. A delayed explosion could alert the enemy. After months of trials, the team produced a compact, portable device, small enough for infantry to carry multiple mines, yet powerful enough to disable even the formidable T-34. Simultaneously, tactics were developed for nighttime deployment. Mines had to be placed quickly and silently on moving tanks or abandoned vehicles, often under cover of darkness or in forested terrain. The collaboration between engineers and frontline sappers was critical. The weapon had to work perfectly in the chaos of battle, not just in controlled lab conditions. By mid-1943, the magnetic mine had evolved from a risky experiment to a practical, lethal anti-tank weapon ready for battlefield deployment. By the summer of 1943, the newly developed magnetic mines were cleared for limited frontline use. The first units to receive them were specialized assault engineer detachments attached to infantry divisions operating near the Bryansk and Kursk sectors. These units, trained in sabotage and close-quarters anti-tank tactics, were considered capable of handling the extremely dangerous task of placing the mines directly on enemy armor. Before field deployment, engineers briefed the sappers on placement points that offered maximum effect. Tests showed that the mine was most effective when attached to the lower hull, the rear engine plate, or suspension components. These locations provided thinner armor and a higher probability of immobilization. Sappers received detailed diagrams and conducted practice runs on disabled German tanks to rehearse silent placement and fast withdrawal. Each soldier carried 3 to 4 mines, timed fuses, and wire cutters for approaching enemy armor through obstacles. Deployment doctrine required complete silence. Weapons were not to be fired, and communication relied on hand signals. Operations were scheduled for nights with low moonlight, when visibility for tank crews was minimal. Reports from the first operational tests were encouraging. Mines adhered reliably, even on muddy, damaged surfaces. The explosive charge consistently disabled tracks or ruptured the engine compartment. Commanders noted that a small group of engineers could potentially stop a much larger armored force, provided they reached the tanks undetected. The stage was now set for a high-risk nighttime operation that would test the magnetic mines under real battlefield conditions against an advancing Soviet column. On the night of the 17th of October 1943, German forward observers detected movement along a forest corridor near Kirov Station, a sector frequently used by Soviet armored units for night advances. Intercepted radio traffic suggested that a Soviet tank regiment, supported by infantry, intended to break through a weakened German defensive line before dawn. The approaching column consisted mainly of T-34/76 tanks, with several KV-1 heavy tanks positioned at the rear. The terrain-dense forest, narrow tracks, and low visibility restricted maneuverability but favored a close-quarters ambush. German command recognized that conventional anti-tank guns would be ineffective in the dark and risked exposing their positions. At 22:40, a detachment of 12 German assault engineers, Pioneer, equipped with magnetic mines, received orders to halt the Soviet advance long enough for German reinforcements to reposition. Their objective was not to destroy the entire column, but to immobilize enough tanks to create a bottleneck that would force the Soviets to halt or reroute. The engineers moved into position along the forest edges where the road narrowed. They established silent observation points, mapping tank spacing and estimating the interval between vehicles. The plan relied entirely on timing. Sappers needed to approach each tank after it passed their position, attach the mines without being seen, and retreat before the explosion. Soviet tank crews advanced cautiously but lacked effective night vision equipment. Engines masked surrounding noise and limited hatch visibility prevented them from spotting movement on the ground. The regiment's confidence in armored superiority made them underestimate the possibility of a close-range sabotage attack. As the first tanks rolled past the German engineers' concealed positions, the sappers prepared to begin their dangerous task. The success of the magnetic mine concept and the survival of the defensive line would now depend on their precision and silence. At precisely 23:15, the German sappers began deploying the magnetic mines. Working in pairs, they approached the tanks under the cover of darkness, keeping low to the forest floor and using the natural shadows for concealment. Each mine was carefully affixed to the lower hull or track assembly, where the explosive charge would cause maximum immobilization. Timing was critical. The engineers used synchronized fuses set to detonate several seconds after placement. This allowed the team to retreat safely while ensuring the mines exploded almost simultaneously. Precision was paramount. Any delay or misplacement could alert the Soviet crews and compromise the ambush. The first set of explosions occurred at 23:42. Tracks were shredded, engines ruptured, and several T-34 seconds were rendered completely immobile. Flames and smoke erupted, causing confusion and panic in the tightly packed column. KV-1 second attempted to maneuver around disabled tanks, but quickly became entangled in the bottleneck created by the ambush. Soviet crews scrambled to react, but the engineers were long gone, hidden among trees. The operation achieved total tactical surprise, demonstrating the lethal effectiveness of the magnetic mines. By the end of the engagement, 22 Soviet tanks had been destroyed or immobilized, halting the regiment's advance entirely. Field reports later praised the coordination between engineers and frontline observers. The combination of engineering, precision, tactical planning, and stealth allowed a small team to neutralize a much larger armored threat without the need for heavy artillery or frontal assaults. This night marked one of the most successful applications of magnetic anti-tank mines during the Eastern Front, establishing a model for small unit sabotage operations throughout the remainder of the war. After the ambush, German commanders conducted a detailed assessment of the operation. Engineers and field officers analyzed the results to determine why the magnetic mines had succeeded so dramatically. Several key factors emerged. 1. Precision placement. Mines were attached directly to critical areas, tracks, and engine compartments, ensuring maximum immobilization and destruction. The timed fuses allowed for safe retreat while guaranteeing simultaneous detonations. 2. Small team coordination. Only 12 engineers achieved what would have required dozens of artillery units in a conventional attack. Well, 1, 2,000. Each sapper had a defined role, minimizing confusion and maximizing efficiency. 3. Element of surprise. Nighttime deployment and the natural concealment of the forest prevented Soviet crews from detecting the engineers, highlighting the importance of terrain and stealth in sabotage operations. 4. Innovative engineering. The magnets used were strong enough to adhere under mud, vibration, and movement. Explosive charges were calibrated for the armor thickness of T-34 and KV-1 tanks, demonstrating precise engineering knowledge applied to battlefield conditions. Post-engagement reports noted that the ambush had disrupted Soviet logistics for several days. With 22 tanks out of commission, Soviet infantry and armored units were forced to reroute and delay their attacks, giving German forces time to reinforce vulnerable positions. Military analysts later recognized the operation as a textbook example of combining engineering innovation with tactical execution. It demonstrated how small, specialized units, equipped with the right tools, could exert disproportionate influence on the battlefield. The success of this operation also influenced later developments in German anti-tank warfare. Magnetic mines became part of the assault engineer toolkit used in urban combat, defensive operations, and sabotage missions across the Eastern Front. The impact of the magnetic mine ambush was immediate, not just tactically, but also strategically. Soviet commanders quickly realized that their tanks were vulnerable to previously unforeseen threats. Reports described sudden, unexplained immobilizations and confirmed that German engineers were using magnetic explosives. To counter this, the Soviets implemented several measures. 1. Anti-magnetic coatings. Newly produced tanks received thin layers of non-magnetic paint to reduce adhesion for enemy devices. 2. Track guards and skirts. Tank suspensions and vulnerable hull areas were fitted with protective skirts, making it more difficult to attach mines directly. 3. Increased reconnaissance. Infantry units and reconnaissance patrols were assigned to sweep narrow roads and forest paths for suspicious objects before tank columns advanced. 4. Crew vigilance. Tank crews were instructed to remain alert at all times, particularly during night movements, and to conduct rapid inspections of exposed armor when stopped. Despite these countermeasures, German engineers continued to refine their magnetic mines. The weapons became smaller, lighter, and easier to deploy, while fuse timing and magnet strength were adjusted to maintain battlefield effectiveness. This ongoing evolution of both offensive and defensive technologies illustrates a key dynamic of the Eastern Front. Innovation often dictated survival. Every successful German operation forced the Soviets to adapt quickly, creating a continuous cycle of tactical and technological escalation. The ambush of the 22 tanks was more than a single tactical success. It demonstrated the broader influence of engineering ingenuity on the war, shaping armored warfare strategies for both sides. The ambush at Kirov Station and the destruction of 22 Soviet tanks marked a pivotal moment in anti-tank warfare. The success of German magnetic mines proved that small, specialized engineering units could have a disproportionate effect on the battlefield, neutralizing heavily armored forces without large-scale artillery support. After this operation, magnetic mines were integrated into broader Wehrmacht anti-tank doctrine. Assault engineer units were trained specifically in their deployment, with operational manuals detailing placement techniques, timing calculations, and escape procedures. Commanders recognized that technology, when combined with precision planning and small unit tactics, could alter the outcome of engagements that might otherwise favor larger forces. The magnetic mine also influenced post-war military engineering. Studies of these devices informed the development of modern anti-tank mines, magnetic limpet charges, and sabotage techniques used in urban and armored warfare. Military academies in Europe and the United States later included case studies of these ambushes, emphasizing the lessons of engineering innovation, stealth, and tactical timing. Historically, this event serves as a clear example of how innovation in weapons technology and battlefield ingenuity can temporarily shift the balance of power, even in the face of overwhelming enemy numbers. The engineers who placed the mines demonstrated skill, courage, and technical expertise, leaving a lasting impact on military strategy and armored warfare. The destruction of 22 Soviet tanks by German engineers using magnetic mines remains a remarkable example of tactical innovation during World War II. It illustrates how small, specialized teams, armed with advanced engineering solutions, could neutralize threats far larger than themselves. The operation demonstrated several key lessons. 1. Engineering meets tactics. The mines were only effective because of precise placement, timing, and coordination with frontline intelligence. Technology alone could not achieve such results without trained personnel to execute the plan. 2. Asymmetrical advantage. Even heavily armored columns could be disrupted by well-planned ambushes, proving that innovation could overcome numerical superiority. 3. Adaptation and countermeasures. Soviet responses, anti-magnetic coatings, track guards, and heightened vigilance highlight the continuous interplay between offense and defense, a hallmark of modern warfare. 4. Legacy for future conflicts. The principles demonstrated stealth, precision engineering, and tactical timing continued to influence military engineering, urban combat, and anti-armor strategies long after World War II. Historically, the magnetic mine operations on the Eastern Front exemplify how ingenuity and technical mastery could change battlefield dynamics. Small teams of engineers and sappers played a disproportionate role in delaying or destroying armored formations, shaping both immediate tactical outcomes and long-term strategic considerations. Ultimately, this operation stands as a testament to the combination of human skill and technological innovation, a defining feature of warfare that would echo throughout the 20th century and beyond. The engineers' work proved that even a few well-trained, inventive soldiers could make a decisive impact against the seemingly unstoppable force of mechanized armor.